Alright, hey guys, so this is a continuation of section 5.6, rational functions, where we're going to go through and graph the function f of x. And so, to graph f of x, we're really looking for a few different things. We're looking for all the x-intercepts, the y-intercept, the horizontal asymptote, if it's applicable, any vertical asymptotes, and the end behavior. And I'm going to show you a really neat table, which is a technique for helping us figure out how to graph these functions. And so the first thing is x-intercepts, and when we're trying to solve for x-intercept, it's the same as it's been for the rest of the entire semester, which is how do you find x-intercepts? Well, you do that by setting y equal to 0. And so since f of x is y, right, it's just another name for y, you're essentially replacing this with a 0. And when is this equal to 0? Well, when the right side is equal to 0. Since the right side is a fraction is only equal to 0 when the top is equal to 0, right? So all we have to really do is set the top equal to 0 and solve. So to do that, we have x minus 2 times x plus 3. And so we're going to set that equal to 0 and solve. And since this problem has already been factored for us, right, it may not always be the case that they give us the factored form. But since this problem has already been factored for us, we know that using the zero product property, two numbers multiply to 0 when if and only if at least one of them is 0, right? And so all we have to do is take inside of the binomials and set them equal to 0 and solve for x. And so x minus 2 equals 0 gives us that x equals 2 will be a solution for an x-intercept, and solving this one, subtracting 3 from both sides, gives us x equals negative 3. So our x-intercepts are the points 2, 0, and negative 3, 0. Okay? Now, how do we find y-intercepts? Okay, well, remember, to find any y-intercept, you find a y-intercept by setting x equal to 0. And so to do that, it's pretty simple. So we say f of 0, right, letting x equal to 0, is equal to 0 minus 2 times 0 plus 3, 0 minus 1 times 0 plus 2 times 0 minus 5. And what we're going to get here is negative 2 times 3 over negative 1 times 2 times negative 5. Negative 2 times 3 is negative 6. Negative 1 times 2 is negative 2 times negative 5 is positive 10. And so negative 6/10, since these are both even, we can divide by 2, and it simplifies to negative 3/5. So our y-intercept is x equals 0, y equals negative 3/5. Cool. Now we're looking for horizontal asymptotes. And so remember, for horizontal asymptotes, there were 3 different cases that we could use to make our life easier. If it was case 1, where the term on the top is larger, then we're going to need to do long division to actually figure out what the end behavior looks like. But for at least horizontal asymptote's sake, we know if the degree of the polynomial on top is larger than the degree of the polynomial on bottom, we won't actually have a horizontal asymptote, right? We'll just have to figure out the end behavior by doing long division. And so, but in this case, we have the degree of the bottom polynomial being larger than the degree of the top polynomial. And maybe you can't see this because it's not in its standard form, but if you were to multiply these first two binomials, x minus 2 and x plus 3, when you do FOIL or distribution, you're only really going to multiply x times x to itself once. And so the degree of this polynomial is going to be dictated just by x squared, right? There's going to be some other stuff up here, but you're only going to multiply x times another x once, and so the degree of the polynomial on top is going to be x squared. And likewise, because the coefficients of all of these guys are 1 here, that same kind of thing is going to happen, and so we're going to end up with an x cubed and some other stuff here. And so if you wanted to see exactly what this polynomial looked like, if you didn't feel like this is explicit enough for you, you can go ahead and expand it. But we are looking at our three cases to figure out our horizontal asymptote. And because the degree of the top polynomial is less than the degree of the polynomial on bottom, we know that our horizontal asymptote is just going to be y equals 0, right? And we covered this in the last lecture. So, well, that makes our life pretty easy. Now, how do we find vertical asymptotes? Well, recall that vertical asymptotes are essentially domain restrictions. So they're numbers that we can't plug into our function. And so numbers we can't plug into our function only come about because of the denominator, right? Because of the numerator, there's no restriction for what kind of numbers can end up at the top. But when we have a fraction, we can't ever have a 0 on the bottom because division by 0 is not allowed. And so really what we need to do is kind of like what we did for the x-intercepts. For the x-intercepts, we took the top, we set it equal to 0 to find our x-intercepts. For vertical asymptotes, you take the bottom of the rational function, set it equal to 0, and solve. And so what that's going to look like is 0 and the bottom of our the bottom of our rational function is going to be x minus 1 times x plus 2 and x minus 5. And just like the top, this one is already given to us in its factored form, but that's not always going to be the case. So you may have to do some work to figure out what the factored form looks like, either using factoring by hand or the new method we learned in section 5.5, which was finding rational zeros of polynomials. Okay, so now that we have these three binomials multiplied to 0, we're going to do the same thing we did for the x-intercepts. You take the inside of each of them, we set it equal to 0, and we solve. The only issue now is these are binomials on the bottom of our rational function, and so these are values that are not going to be in our domain, right? And so let me go ahead and write what the domain should be here. Okay, and so x minus 1 equals 0, we add 1 to both sides, we get x equals 1. Okay, so we can't have x equal 1. X plus 2 equals 0. We don't want it to equal 0, so we can't have x equals negative 2. And add 5 to both sides, we get x cannot equal positive 5. So our vertical asymptotes are x equals 1, x equals 2, and x equals 5, right? So these are the vertical dotted lines that are going to be on our graph to let us know what lines we shouldn't cross. And likewise, our domain is going to be a restriction of these values. So we can't use 1, negative 2, or 5. And so our domain is going to look like negative infinity all the way to negative 2, union negative 2 to 1, union 1 to 5, union 5 to infinity, right? And so that's what the domain of our rational function looks like. And because we do have a horizontal asymptote, our end behavior is going to be mimicking that horizontal asymptote. So really, the end behavior is only going to require some calculation if we end up in case 1, which is when the top of the degree of the top polynomial is larger than the degree of the bottom polynomial. And so since we didn't end up in that case, we just know as x approaches negative infinity, y approaches 0, and as x approaches positive infinity, y is also going to approach 0. So that makes it really nice for us. Okay, so now we have essentially everything we need to graph this function. However, we're also going to create a table to make our life even easier. And so this table is going to use all the values you find in the vertical asymptotes and all your x-intercepts, okay? And so, and if you have it, it will use your horizontal asymptote as well. If you don't have a horizontal asymptote, this will be replaced by the end behavior. And so how the table works is you're essentially going to create a number line that consists of all the x-intercepts and the vertical asymptote. So you start at negative infinity, and then what is our next smallest number? Well, we have 1, -2, 5, 2, and -3. So -3 is next. And then we have -2. And then we have 1. Then we have 2. And then 5. And then after that, we have positive infinity. So we're essentially creating a number line that consists of our vertical asymptotes and our x-intercepts. And so you could list them. So we had 2, -3, 1, -2, 5. And so you can see that I've essentially just put them in order, but also including positive and negative infinity. Okay, so what you're going to do on the left here is you're going to put all of the factors that made these 0. So for instance, we got -3 from the numerator, right, from setting the top equal to 0, which came from the binomial x plus 3. So that's what we're going to put here. We're going to put x plus 3 here. Okay, where did we get -2 from? Well, that was a vertical asymptote we got from the binomial x plus 2. And so we're going to list that here. And you're essentially going to follow the same order except drawing vertically. And so we got 1 from x minus 1. We got 2 from x plus 2. And we got 5 from x minus 5. Okay? And so now we can draw some horizontal lines to kind of make our table look a little neater. Hopefully your lines will look a little straighter than mine. And then what we're going to do is put some vertical lines here. Okay. And so what you're going to do at this point is, I suppose these ones aren't necessary. Okay, so this is essentially a table that's going to be used to figure out whether our graphs are above or below the x-axis. It's just going to help us be more accurate with our sketch. And so remember that -3 was the number that gave us x plus 3 as a 0 for the top of our rational function. And so if you plug in -3, what you'll get is 0, right? But if you plug in something like -4, something on the left of -3, into our function here, you would get f of -4 is equal to -4 minus 2, -4 plus 3, -4 minus 1, -4 plus 2, -4 minus 5. And so the top number is going to be -6 times -1 divided by -5 times -2 times -9. Negative times negative is going to be +6. Negative times negative times negative is going to be a positive. 9 times 5 is 45, times 2 is 90. So we're going to get -90. These are both divisible by 3, and so we're going to get 2 over 30. These are both divisible by 2, and so we're going to end up with -1 over 15. And notice that the answer at the end is negative, right? Okay, well, we don't want to have to do this over and over for a whole bunch of different values, and so this is what the table essentially aims to solve, is that notice we plugged in -4 and we got a negative number, right? Well, that tells us that if you plug in anything to the left of negative 3, you're going to get a negative number, right? Because negative 3 plus 3 is 0. Let me draw this table again. So the lines shouldn't be between the points. Got a little ahead of myself. The vertical lines should be going through the points. So they should look more like this. Something like that. Okay. Sorry for this terrible lines here, guys. I'm sure you get the idea. And so since we plugged in negative 4, right? And negative 4 lives in this box, and it ended up giving us a negative value. Well, that's because negative 4 is the thing that makes every single one of these binomials equal to a negative. And so it makes this one negative, it makes this one negative, because negative 4 is larger than all of these positive ones, right? It makes all of these negative, and when you take these 5 negatives and multiply them to each other, you're going to end up with a negative. So our rational function, f of x, is going to be negative in this interval from negative infinity to negative 3. And so rather than having to do all of this plugging and chugging of numbers, it's always going to follow this behavior. So negative 3 is what made this one 0, and so everything to the left of it is going to be negative, right? Like negative 4. And if I were to plug in, let's say, like 0, 0 is on the right of x of negative 3, so it's going to be positive here. Okay? And so the way this works is you kind of just put open circles, which is, I mean, it's a 0. Anywhere you have the binomial equal to 0, since negative 2 makes this one 0, we put an open circle here. 1 makes this one 0. Okay? 2 makes, this one should be x minus 2, right, from the numerator. Yeah, okay. So good thing I caught that mistake. No, this one is plus 2. This one's minus 2. Okay. And so this is the value that makes this binomial 0. And 5 is the value that makes this binomial 0. And so you essentially put zeros everywhere where they match up. And you think of each of these horizontal sets in our table as just being a number line. And so if you're 0 here, then to the left you're going to have negative numbers, and to the right you're going to have positive numbers. And really what's happening here is any number that's larger than negative 3 is going to make this entire binomial positive, and that's essentially what the first row is saying. Okay? And so if it's to the left of the 0, you put negatives. If it's to the right, you put positives. And so hopefully this makes sense. If it doesn't, go ahead and ask me in office hours. And so this just makes it so we don't have to do all that plugging and chugging like we did for the number negative 4. It's a lot easier to just figure out what the zeros are and make this positive and negative table. Okay, and then to figure out the values for f of x, it just becomes a counting of how many negatives you have. If you have an odd number of negatives, like this one, 1, 2, 3, 4, 5, well, an odd number of negatives is going to make a negative. And here we have 4 negatives, but 4 negatives multiplied to each other is going to make it positive. Here we have 3 negatives, so we're going to end up with a negative. Here we have 2 negatives, which is going to make it positive. Here we have 1 negative, which is going to make it negative. And here we have all positives, so this one's going to be positive. And so now we can finally get to graphing our rational function. Okay, and so what we're going to do is we're going to put all our x-intercepts and vertical asymptotes. So first we're going to plot our x-intercepts, which we have as positive 2 and negative 3. So positive 2, 1, 2, we have an x-intercept there. and negative 3. 1, 2, 3. Okay. Then we're going to plot our y-intercept, which is 0, negative 3/5. So it's close to negative 1, maybe halfway between. And so we're going to have negative 3/5 somewhere right about there. We're going to look at our horizontal asymptote, which means our horizontal dotted line is y equals 0. So we know our x-axis is going to be that dotted line. Okay. We have a vertical asymptote at x equals 1, x equals negative 2, and x equals 5. So x equals 1, we have a vertical asymptote. So we're going to have dotted lines here. We have it at x equals negative 2. And we had it at x equals 5. So another set of vertical lines. Do we have any other information? Well, we know our end behavior is taken care of because of our horizontal asymptote. And here, we're just going to use our table. So we know from negative infinity, right, which is all the way over here, to negative 3, our numbers are going to be negative. So we're going to be starting below the x-axis like this. And since we have to cross, we have an x-intercept here, right? We have to cross. Oh, excuse me. Let's see. So from negative infinity to negative 3, it's always going to be negative. Okay, so like I was saying, from the interval negative infinity, which is here, to negative 3, we know our numbers are negative, right? And so we know we're going to be below the x-axis. We're going to be hanging on over here because our horizontal asymptote is 0. And so all the way to here, our numbers are going to be negative. So we know we're below the x-axis. Then we get to our x-intercept we have to cross. And then we see that from negative 3, right, which is this point, to negative 2, so negative 3 to negative 2, our numbers flip and become positive. And that's because we're crossing the x-axis, and now we're going to follow our vertical asymptote all the way up, right? Because we can't go up and come back down because we can't cross this vertical asymptote, right? And because it has to be a function, we have to pass the vertical line test, so this is the best that we can do. And then what happens now is, well, from negative 2, which is this vertical asymptote, to our x-intercept 1, we know that we are below the x-axis. So we know we're going to cross here because we have a y-intercept, but we know between negative 2 and positive 1, we are negative. So it's going to be somewhere over here. Okay, and then we cross the y-intercept. And because we know we're going to be negative on this interval the entire time, right? Because that's what's happening between negative 2 and 1, we know that we can just send our function right back down. Okay, so there are 2 arrows. Now for our next interval, which is between positive 1, which is our vertical asymptote, and 2, we know we're positive, right? So that means we have to either start up here by this vertical line or down there, but because we're positive, we know we start up here. And then we're going to come down and we're going to touch our x-intercept, which is at 2. And then from 2 to 5, we know that we're negative. Okay? So from 2 to 5, so this x-intercept to this vertical asymptote, we're negative. And so we know to just stay under the x-axis, and we know to stay there really because we don't have another x-intercept, but also because it tells us that we're negative. So our arrow is going to come and follow this. And then we have that between 5, right, which is this vertical asymptote, and infinity, we're going to be positive. And so since we have to follow the vertical asymptote either down here or up here, we know it's going to be up here. And since our horizontal asymptote is 0, we know it's just going to hug the x-axis, and so we can draw our arrow is getting really, really close to it. And so this is a sketch of our rational function f of x using this table, which helps us kind of figure out where our line should be starting, and all of the information that we came up to here. So we needed to find the x-intercepts, the y-intercepts, the horizontal asymptotes, if they're applicable, the vertical asymptotes, and then the end behavior is given to us by the horizontal asymptote. If we weren't in this case, and we were in the case where the degree of the top polynomial is larger than the degree of the bottom polynomial, then we would need to do long division to figure out what the end behavior was and figure out where our arrows are going to end up. And so this is a pretty good sketch, and so I will place a picture of what it looks like graphed on a graphing tool in 1 second. Okay, and so now you can see this picture that I've pasted in the upper right here, which overlays, and this is Desmos, and so you can see how useful our information becomes because we're able to get a pretty good sketch of what the rational function looks like without needing any sort of graphing utilities. And as you eventually end up taking calculus, you'll be able to get your sketches closer and closer to what Desmos is drawing here. But hopefully this was helpful. If you have any questions, go ahead and let me know via Discord or via office hours, and I'll see you in the next one. Later.